Okay, let's start with the key concepts related to multiple regression. So we know that in the last lecture, we have already studied simple regression, where you only have one independent variable in the regression model. And multiple regression refers to the situation where you have more than one x variables or more than one independent variables in your equation. Like here, you might have x2, x3, x4, so on and so forth. So if you want to explain the meaning of the coefficients in a multiple regression model, in particular those coefficients for the independent variables, they also mean the marginal effect of one unit change of the x variable on the y variable, holding other things equal. So this holding other things equal is just something new on top of the simple regression model. So basically, just recall that when we want to explain the coefficient of a single independent variable, it means that when x increases by 1 unit, how does y change in response to the change of x? And here, because there are multiple x variables, so when you explain it, you should say that the marginal effect is when x increase or change by one unit, what is the change of y, holding other x's, holding other independent variables unchanged. So just to make sure that when you explain the marginal effect, you highlight that this is the marginal effect holding other things equal. Okay. All right. And consider when you estimate a model of a multiple regression, you have, if the true model is y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus e, and the result is that y hat is equal to b1 plus b2 x2 plus b3 x3. And so in this case, as the same as the simple regression models, B1, B2, and B3, they are the estimators of the true parameters beta 1, beta 2, beta 3. So they are also random variables. They have their means. And of course, when the basic assumptions of OLS are satisfied, they are unbiased estimators. So the mean of B1, B2, B3 should be the same as beta 1, beta 2, and beta 3. And in this case, the variance of B2 will be equal to sigma squared divided by, in bracket, 1 minus R23 squared, and times the summation of the squared deviation of x2 from its mean. So, well, this is a complicated equation. You do not really need to know the kind of a specification of the equation, but the most important thing is that you should know what it means. And here, this part, 1 minus R23 squared, is something new compared to what we studied in lecture 3. So in lecture 3, basically the variance of B2 is just this part without 1 minus R23 squared. And R23 squared is the correlation coefficient between x2 and x3. So basically, R23 is a measure of how closely the two independent variables, the two x variables, are correlated. And from this equation, we can see that the variance of B2, so the variance of B2 is a measure of basically how inaccurate B2 is, or how noisy B2 is as an estimator of the true parameter B2. We see that the variance of B2 tend to be larger when sigma squared, the variance of the error term, is larger. This is very simple. This is very easy to understand. This is also the same as the property of simple regression estimators. So basically, when the variance of the error term is larger, it's harder to get accurate estimation of B2. So basically, the B2 tend to be less accurate. Okay. The variance of B2 also tend to be smaller when n is larger, when the sample size is larger, because when sample size is larger, this part is also larger. So when you have larger sample, you always tend to have more accurate estimation of B2. And the variance of B2 tend to be smaller when the x's are more spread out. So basically when the variance of x, when the variance of the independent variable is larger, it's easier to get better estimation of B2. This is also the same as the property of B2 in a simple regression model. And finally, the fourth one is really something new in this lecture. So I think the first 3.1, 2, 3, they are already there. They are already the properties of the parameter B2, the estimator B2 in a simple regression model. So the fourth one is really something new. So it says that the variance of B2 tend to be larger when the R23 thing is bigger or when the x's are more correlated. So mathematically, it's not so hard to see. When R23 is larger, then R23 squared also tend to be larger. So 1 minus R23 tend to be smaller. And when the denominator tend to be smaller, the whole fraction, the value of the whole fraction tend to be bigger. So this is how to see it from mathematical point of view. And from intuition point of view, we can also see that when x2 and x3, roughly speaking, when they are more correlated, then it's a little bit harder also to see how much each of them explain the movement of y. And in particular, when we study the later part of the chapter, you will also see that when R23 is equal to 1, which means that when x2 and x3 are perfectly correlated, then actually that will make a big problem for your estimation. Mathematically, you can see that when R23 is equal to 1, so this 1 minus 1 is 0. And something divided by 0 is actually undefined. It makes something what we call an explosion of the variance. And from econometrics point of view, we also have the concept calling it collinearity. So when there's collinearity, it makes it such that the estimation is so noisy and you just cannot do the estimation at all. So basically, the key message here is that the estimator of beta 2, the estimator B2, tend to be less accurate when the independent variables are more correlated. Okay, and after that, we also want to introduce the concept of R-square. Well, I think most of you probably have already studied R-square in previous courses. Just to basically go over again what you have studied. We know that, so since from the regression model, y is equal to y hat plus the estimated error term, so the residual. So the true value of y should be equal to the estimated y plus residual. And hence, due to the property of OLS, we can also know that the squared deviation of y from its mean should be equal to the square deviation of y hat from its mean, and also plus the summation of the square of the residual. And here we call them using different names. We say that the summation of the square deviation of y from its mean, we call it total sum of squares, or SST. And the summation of the square deviation of y hat from its mean is called the sum of squared explained by the regression. So in this textbook, we call it SSR. And the sum of square of the residual or square errors is called SSE in this textbook. I understand that maybe in a different textbook, these two terms are named differently. Some of the times they also call this sum of squares residual, so this is called SSR and so on. So to make it more workable for this course, we stick to the definition in the textbook, but you just need to understand the meaning of the concept, and you don't need to be very accurate about how it's exactly named. Okay, so R squared is defined as the sum of squared explained by the regression divided by the total sum of squared, or 1 minus the sum of square errors divided by total sum of squared. Usually, R squared is a number that is between 0 and 1, and the meaning of it is the proportion of variation of y. So like this is the variation of y, the fluctuation of y. It's interpreted as the fraction of the variation in y from its mean that can be explained by the model. So basically, we want to use y hat to explain the movement of y. So basically, the fraction of this term divided by this term will be the part of the variation of y explained by the regression model. Okay, and I want to highlight here, maybe in some introductory courses, you usually use R-square as a very important measure of the kind of fitness of the model, and usually you compare two models, you think that the model with bigger R-square are surely better than the others. But I think from this course point of view, I would like to say that at relatively more advanced level, so we usually consider R-square just as a descriptive measure. Okay, so of course, it helps you to see the fitness of the model, but you shouldn't just use it as the sole measure of how good a model is. Okay, so it's not that deterministic of how good a model is. And we should also know that R-square tend to be different for different types of models. Usually, for cross-sectional models, R tends to be not so high. And it can be the case that very good cross-sectional models may only have an R-square around 0.1. Well, on the other hand, if you look at time series models, it's also pretty likely that even when you have a not so good model, you still have an R-square which is larger than 0.8. So in this case, you should surely know that you shouldn't use R-square as the single measure of comparing models. Okay, and finally, we want to introduce another concept related to R-square, which is called adjusted R-square. So basically, for multiple regressions, when you add more variables, when you add more independent variables, as long as the new additional variable helps to explain y variable a little bit, R-square always tend to increase by at least a little. So basically, when you add more variables into multiple regressions, R-square should either increase or stay the same. And in this case, R-square always tend to favor large models. That's how we call it. So basically, because when you add more variables, you always tend to have increasing R-square. So if you just use R-square as a measure of judge how good a model is, larger models always appear to be better. And in this case, it is probably useful to get a measure which is kind of fairer to small models, or a model that can, a measure that can provide a fairer ground for comparing the fitness of big and small models. And adjusted R-square is just something like this. Again, it's defined as this equation. You don't need to remember the exact specification of the equation. You just need to know the most important intuition here is that because we know when you have more variables in your model, R-square always tend to increase. So in the adjusted R-square, we introduce something like a punishment term for the R-square such that when you have more variables in your model, you get more punished. And in this case, because we have this punishment for larger models, this adjusted R-square provides a fairer ground to compare small and big models, because big models can be punished, and if the additional explanatory power of the new x variables is not sufficiently big, then the adjusted R-square might be smaller for bigger models than for small models.